So we've talked about first-order differential equations and a lot of different kinds of first-order differential equations that we can solve. Now we want to move into higher-order differential equations, and we're going to very much narrow our focus. Things get much, much more complicated. And so we're going to say, look, we're only going to deal with the nicest settings. And so what does that mean? Well, we're going to look at what we call linear. So we say an nth order linear differential equation is anything which can be written as you have the nth derivative, so that notation means nth derivative, and that's what we mean by nth order. So that's not a coincidence that these match. So the highest derivative is an nth derivative plus something which can depend on x times the n minus first derivative, and keep going, something which can depend on x first derivative, something which depends on x, y equals an arbitrary function f of x. From now on, we're only going to work with these linear differential equations. And there's going to be more or less two categories. Now, the nice category is what we call homogeneous, and that's if this right-hand side is 0. The non-homogeneous is if this right-hand side is not 0. Now, you might say, wait, we already have something we called homogeneous before when we talked about substitution. Yes, it's the same word, but means something else. And I know that's not the best situation, but we had to do a little bit of recycling in math. So don't get too confused by this. So here, homogeneous says this right-hand side is 0. So you really should think of it as you have a left-hand side and a right-hand side. And now, in addition to saying we're going to narrow, we're going to really narrow, and a lot of our energy is going to be in a very special case where we talk about constant coefficients. And what that means is that these functions showing up are all numbers. We'll still let f of x be arbitrary, but now that's a very special thing. So it's just derivatives of numbers on the left and function of x on the right. And that's where we're going to spend a lot of energy in the next week. Now, as before, you might ask questions such as, do solutions exist? Are they unique? And the answer is yes. They do exist, and they are unique as long as you're being reasonable, which is to say, if you tell us some initial conditions, and so what we have is some values at a particular point A. We know the value of the function, the derivative, all the way up to the n minus first derivative. Now, you should think of it as saying, this tells us where we are. Or you might say, it tells us our current state. It tells us position, velocity, acceleration, So if we know our current state, and we have our differential equation, which tells us how we change, between those two pieces of information, we know where we are. And we will continue to persist to know where we are up to and as long as these pieces that make up our differential equation are nice. So good. All right. So that's the idea. Off we go into higher order differential equations. One of the things that we get by restricting to these linear differential equations is the following. If we have our homogeneous differential equation, remember homogeneous meant that right-hand side is 0, and we have some solutions. Well, we can make new solutions by doing a combination, and namely arbitrary constant times the first, arbitrary constant times the second, so forth and so on, all added together. And we actually have a very particular name for this, and what we call this is a linear combination. Now, we've been throwing this word linear around, and so we should stop and say, okay, why are we throwing this word around? What is it about linear? And the punchline is linear really gives us two important things. It gives us the ability to add, and it gives us the ability to scale. So when I talk about add, it says, oh, if I have this and I have that, I can add them together. Put a plus sign. Scale says if I have this, I can throw a number in front. So I can do like 5 times that, or 10 times that. And so you'll see what we're doing here is we're scaling, that's what the C's, and we're adding, that's what the pluses are. And so linear says, hey, if I have something, I can take linear combinations and I still have something. So great, great. Now, it turns out you can go one step further and say, well, suppose that you have a nice collection of functions. Now, there's a couple of things that make a collection nice. Namely, it's how big is your collection. You'll notice here we have up to, we put y sub n, meaning we have n solutions, and that n matches with that n. In other words, the order of the derivative matches with the number of solutions. And there's something called linearly independent. Now, we're going to talk about linearly independent in just a few moments, but for now, the key idea for linearly independent, you should think about it as being, they're fundamentally different. So, in other words, it's not like I'm repeating anything I already have. So each one of them gives me something brand new. So if we have a nice collection, then not only do we have lots of solutions, because we can always do this action, but we have all solutions. Every possible solution is of this form. And the basic reasoning is, it turns out, you can say, look, once we have these collection of solutions, then we can satisfy any initial condition by choosing the right values for your C's. And remember a few minutes ago, we talked about existence and uniqueness. And uniqueness said, hey, there's just the one. And so since this works for some right values of C, then it has to be the solution. So every solution is accounted for. So now what this tells us is thanks to superposition, it really says, hey, we don't have to find every possible solution that exists. We just have to come up with a good set of solutions, and then every solution is a combination of them. Now, I will say there's another word I sometimes like to think of in terms of superposition, because superposition is a very strange one. I also like to use the word stacking. It's really what we're doing is we're putting all these solutions together. And that's going to be our go-to tool. So why does this work? All right, so here's a basic argument. And we'll just do a very simple case. And the general case is similar. It's just a lot more notational, inconvenient to work it out. So let's just suppose we have solutions, y sub 1 and y sub 2. Well, to say that there are solutions means that when you plug y sub 1 into that left-hand side, you get 0. And when you plug y sub 2 into that left-hand side, again, you get 0. So now we're going to take a linear combination, some constant y1 plus some constant y2, and we're going to plug it in. So that means we're plugging it into the left-hand side, and let's see what comes out. So we plug in everywhere where we see a y, we replace it by this function. And now we use a nice fact, which is to say that derivatives are linear. They respect addition, which means if I have two functions and I want to take the derivative, I take the derivative of the first plus the derivative of the second. All right, and also if I have a constant times a function, so if I have a constant times function, then the derivative is that constant times the derivative of the function. All right, great. So what happens? So the nth derivative is the c1 times the nth derivative of the first function, c2 nth derivative of the second function, and all the way down. All right, now just combine. Well, in other words, say, look, I'll grab everything which had a c1, and so we have a bunch of terms, and we'll put them together and factor the c1 out. So we have nth derivative, a sub n minus 1, n minus first derivative, all the way down a0 times y1. All right, so there we go. There's that. And then we'll do the same thing with the c2 pieces. So everything with the C2, we're going to take all those, combine them together, pull out the C2. So we have C2 nth derivative of y2. Then we have it pulled out, a sub n minus 1 of x, n minus first derivative of y2, da 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 da, all the way down, a0 of x, y2. And now our great aha is to say what? Well, our great aha is to say, well, we know that these two pieces here are 0. So this becomes c1 times 0 plus c2 times 0, and that, of course, gives us in the end a grand total of 0 plus 0 is 0. So it's still a solution. And so this is why we like linear differential equations. It helps us reduce the workload. And we like having it be a little bit simpler. So let's just take a second and have another way that we can think about what it means to be linear and what it means to talk about superposition. So let's just simplify our setting. Y double prime, a of x, y prime, b of x, y equals 0. So what are we going to do? Well, now what I want is to say, let's not think of it as something equals something, but rather let's think of it as we have the left-hand side, and the left-hand side is actually a machine. And so what happens? Well, what happens is, of course, you have a machine, you have an input, you can put something in, and then you have an output, something comes out. So here's the left-hand side. And in this particular case, what we do is we're going to put in a function which we call y. All right, so in comes a function y. And what comes out? Well, what comes out is y double prime plus a of x, y prime plus b of x, y. And now, to solve the differential equation is to ask the question, well, for which value of y, when we put it into our machine, do we get our output to be 0? So that's another way to think about solving a differential equation, is finding that special value for y, which does it. Now, what's going on when we talk about things like linear and superposition? Well, in that case, what you can think of is you have the following. You say, well, we have something as linear if this is true. So namely, you have our machine here, same machine, and here's our left-hand side. And now what we are going to do is we're going to plug in a linear combination, C1, Y1, C2, Y2. And that goes into the machine. And we say linear is the following. This is equal to C1 times something plus C2 times something, namely, and this is, of course, you have to do this slowly because we're actually drawing the pictures. Okay, so we say something is linear if when we plug it into our machine, we can break up addition and we can pull out the constants. And so that's what's going on. So that's what it means when we say something is linear. And why is this nice? Well, as we were saying, our goal is to find a 0. So if y1 were to output a 0 and y2 were to output a 0, then the whole thing would at the end be 0. And that's what we're after. So this is why we call things linear differential equations, because when we plug in linear combinations into the left-hand side, we really are taking linear combinations of the individual pieces being plugged in, and that's what makes things work out so nicely. So let's do an example. Verify that e to the x and x e to the x are solutions to y double prime minus 2y prime plus y equals 0. Then find the solution, y, which satisfies y of 0 is equal to 5, and y prime of 0 is -3. All right, well, let's do the first part, right? There's 2 steps. There's a verify and there's a find. So we'll start with e to the x. So we have y is e to the x. The derivative of e to the x is e to the x. The second derivative of e to the x is e to the x. Ah, this is why we like e to the x. Now, on the other hand, if we had x e to the x, well, y would be x e to the x. Y prime, well, first times the derivative of the second, which is x e to the x, plus the derivative of the first times the second, which is e to the x. We can also write this as x plus 1 e to the x. Y double prime, well, the derivative of x e to the x, well, same rule, x e to the x plus e to the x, and then add the derivative of e to the x, which is e to the x, and you can again pull out an e to the x and you get x plus 2 e to the x. So now we have our derivatives, we can take combinations. So what do we want? We want one of the y's, we want -2 of the y primes, and we want 1 of the y double primes. So when we do that, we have y double prime -2y prime plus y is equal to, well, we have an e to the x -2 e to the x, and then plus an e to the x. Well, we have e to the x -2 e to the x plus e to the x, which is 0. All right, good. So that verifies that e to the x is a solution. We'll do the same thing over here. X e to the x. We'll need one of the y's, because there's a coefficient of 1. We'll need -2 of the y primes. All right, because coefficient -2. And we'll need 1 of the y double primes. And so when we add these up, we get y double prime -2y prime plus y. Well, that's equal to, okay, so y double prime will be x plus 2 e to the x -2 times x plus 1 e to the x, and then plus 1 of the x e to the x terms. All right, so there we go. Now everything has an e to the x, so we can pull that out. And so what do we have? We have x plus 2 here. Here we can distribute the -2. So that makes it a -2x minus 2. And then here we have a plus x. All right, x minus 2x plus x, 0. 2 minus 2, 0. So that gives us e to the x times 0, which is 0. So again, it checks out. So these are both solutions. Now, is either one of them the correct function? Because maybe that's possible. Maybe they said, okay, hey, here are 2 solutions. Maybe the solution we want is one of these 2. So let's check. When I plug in 0 for e to the x, do I get 5? No, I get 1. Okay, so it's definitely not that one. All right, maybe if I plug in 0 for x e to the x, do I get 5 then? No, 0. Oh, wait, so neither of those are the right solution. Okay, but that's the whole thing about what we're doing. Is not to say, well, great, now we have to find some mysterious solution which, we'll never be able to figure out. No, we're after a solution that we can figure out. That's the whole goal. And what do? We use superposition. So in other words, we have 2 solutions, and we just say their powers combined, right? We put them together. So now we say, let's look at a solution which looks like some constant, I'll use a, times our first solution, e to the x, plus some other constant, which I'll use b, x e to the x. And each one of these functions, regardless of our choice of a and b, is a solution to the differential equation because it's homogeneous, equals 0, and linear. So those are the two things. When we have homogeneous and linear, we can stack our solutions, use superposition. Now the question is, can we set A and B so that we're just right? Well, we need something about y. Also need something about y prime. So what is y prime? Well, that's a e to the x plus b. Now the good news is I know take the derivative of y prime already. So that's x plus 1 e to the x. All right. So for our initial conditions to work, what needs to be true? Well, now we know we need that y of 0, which is 5. Plug it in. 0. That's a times 1 e to the 0 plus b times 0 e to the 0. Okay, so I'm going to need that a equals 5. Aha! I think we can solve for a. But we also need what? Y prime is 0. Well, that should equal -3. So -3. And what should that be? Well, a, and then we'll have plus b. 0 plus 1 is 1 e to 0. So a plus b. And so now our great aha, a equals 5. And we can plug in a equals 5 here, subtract, and this tells us b would be -3 minus 5, which is -8. And so our answer then says choose the values 5 and -8. So the solution that we are after is 5 e to the x minus 8x e to the x. And we're done. So that's it. So that's why we can have success. Good, good. Now in the previous problem, there was a little kind of hidden thing that we used but never actually stated, which is we had these two solutions, e to the x and x e to the x, and we used superposition, and that's totally valid. But how are we somewhat confident that we would get the right answer? Other than that they asked us to, so if they ask a question, there's probably a way for us to get the answer. Well, that comes back to what we mentioned before about linearly independent. And remember, linearly independent means fundamentally different. Now there's a technical term. So we say things are linearly independent if the only way we can take a linear combination, remember that means you can add and then you can scale, and get a 0 as the output, is if all of your choices for your scaling factors were 0. All right, great. So that's a technical definition. Don't stress too much about that. There's a whole course about this. Linear algebra, great stuff, wonderful stuff. And I highly recommend it because linear algebra is the foundation of a surprising amount of mathematics that we do. All right, so we're going to talk about how we can actually test for linearly independence. And it comes down to something called the Wronskian. And what does it do? Well, for two functions, what you do is you take your functions, y1, y2, and you set up a small matrix. y1, y2, so the first row is the function, y1 prime, y2 prime. Second row are the derivatives. And now you're going to take the determinant. Sometimes we take the determinant by putting what looks like absolute value signs on either side. And what do? To take the determinant of a 2 by 2 matrix, well, you multiply. You have down the diagonal, so that's y1, y2 prime, and then up, but in that case you subtract. So y1, y2 prime, subtract y2, y1 prime. And that's the Wronskian of two functions. If you have more than two functions, well, it's just a bigger determinant. And what do? Well, you make a matrix. The first row, the functions. The next row, the derivatives. The row after that, second derivatives, the third derivatives, and you keep going until you end up with the square matrix and take the determinant. Now, the fun fact. If they're linearly dependent, then that says the Wronskian must be 0. So if you do this computation and at the end you get 0, then it's like, oh, I have things which are not fundamentally different. On the other hand, if you take the Wronskian and you get something which is non-zero, then they're linearly independent at that point. And indeed, they're going to be linearly independent up to the point where the Wronskian is 0. And when the Wronskian becomes 0, all bets are off. So essentially, you lose your guarantee of uniqueness and possibly existence whenever the Wronskian goes to 0. But that's a story for another day. So what we're looking for with the Wronskian is a simple question, 0 or non-zero. And so now we have a test. Now, I want to step back and say, what do we mean when we say things are fundamentally different in terms of solutions to differential equations? Well, a very simple example. Suppose I say, hey, x is a solution and 2x is a solution. Are these fundamentally different? Well, you might say, well, that's twice as big. But when you think in terms of superposition, so when I think of ax plus b2x, well, say, well, look, I can combine this a plus 2b times x, and these just come together and combine. So this is a case when what we have is we have sort of a collapse that really, look, we don't have things which are distinct. They're the same thing for all intents and purposes. And so in terms of the definition, what we can say here is it says, well, look, if I chose a equals 2 and I chose b equals minus 1, what would happen? I'd have 2x subtract 2x and I'd get 0. So that's what this means when it says, hey, if you have something where the coefficients are not 0, that really there's some way to combine them to collapse things down. So that's what we mean when we're talking about distinct. That's why we care about these types of questions and why we really want to make sure things work out fairly nicely. So let's do an example where we compute the Wronskian. And in particular, let's do it for x sine of x and cosine of x. All right, so what do? So we're after the Wronskian. We usually denote this with a w. And we have of x sine of x, comma, cosine of x. Now, because we really care about the 0 versus non-zero nature, then it doesn't matter which order we take things in. So if you do the Wronskian of cosine x, x sine x, the only thing that will change is the sign. So don't worry about like, oh, did I get this in the right order? It's okay, it'll work out. So we're going to set up our matrix that we're going to take the determinant of. So the first row are the functions. Now, looking ahead, x sine x, I'm going to use the product rule, so I'm going to give myself some space here because I need to take a derivative, and cosine x. Okay, so functions go in the first row. Next row are going to be derivatives. So product rule. First, x times root of the second, well, that would be x cosine of x, and then plus the derivative of the first, 1, times the second, which is sine of x. So that's function derivative. Cosine of x, the derivative is negative sine of x. All right, so now we need to compute this determinant. All right, so we're going to have our two diagonals. So x sine x multiplied by negative sine x, subtract, go the other way, we're going to have x cosine x plus sine of x times cosine x. And don't forget you need that subtract. And this is a good time to have parentheses. Parentheses are friends. Whenever you have a sign, you want to have a parenthesis in there because that just makes sure things work out. You don't lose any signs, and especially don't lose any points. All right, so distributing through, we'll have minus x sine squared x. And here we'll get a minus x cosine x times a cosine x. So minus x cosine squared x. And then we'll have a minus a sine x cosine x. Well, we can take advantage of the sine squared and cosine squared are both multiplied by negative x. So if you factored that out, that would become negative x times sine squared plus cosine squared, which leaves us with simply minus x minus sine x cosine x. And there we go. So that's our Wronskian of these two functions. What do we do with it? Well, we ask some questions. Like, for example, is it 0 or non-zero? And if you look, when you plug in x equals 0, you're in trouble because you get 0 and 0. And what that's telling you is that at 0, things are not quite as distinct as you'd like them to be. So there's some sort of loss of uniqueness. And so that's why we care about the Wronskian. But away from 0, we're actually okay. And so, all right, great. And now we know something about these functions. Good, good. Now, at the beginning, we mentioned constant coefficient. And this is where we're going to have success, because it turns out that we have a strategy. And we kind of did examples like this already. So if you recall back to when we talked about verifying a differential equation, we said, well, we can plug in a guess and then refine our guess based on the answer. So in particular, if we have something, and for simplicity, we'll do second order, ay double prime plus by prime plus cy equals 0, and we look at the solutions, well, we can guess e to the rx, and when you plug that in, what happens is, well, you'll get an a r squared e to the rx, b r e to the rx, and c e to the rx, and you factor out an e to the rx, and you say, oh, we just need the ar squared plus br plus c equals 0. And so you say, oh, well, that's interesting. If we write them down right on top of each other, what do you see? Well, they look very similar. They are. You say, this is a differential equation. This is an algebra equation. And you can convert back and forth, right? You can see, oh, second derivative, r squared. First derivative, r. No derivative, 1. And the coefficients just go down. And so now we say, okay, we can reduce to solving this algebra problem. And what do we get? Well, if the roots aren't distinct, so we have r1 and r2 are our roots, then we have solutions that look like e to the r1x and e to the r2 of x. Now, here's the nice fact. E to a constant x is linearly independent from e to a different constant of x. So these are, in fact, all solutions have this form. So that's great. And so life is good. So now we can completely solve any differential equation that looks like this. Well, of course, if the roots are distinct. What happens if the roots are not distinct? In other words, they're the same root. Well, the problem is, we've talked about this a moment ago. If we look at c1 e to the rx and c2 e to the rx, we say, well, look, these aren't fundamentally different solutions. We can just combine them together. So that's not going to work. So you have to do a little bit of gentle massaging and say, okay, how do we make it work? What's the right idea? Well, the answer is we modify, you add an x. And so if the roots are the same, e to the root x is the first solution, and then x, e to the root x, is the second solution. Now, give me a second here. I'm going to pull up a problem we did on a previous slide. This problem right here. Verify that e to the x and x e to the x are solutions. Well, if you think about this differential equation here, we have y double prime minus 2y prime plus y equals 0, then the corresponding algebra problem is r squared minus 2r plus 1. Or if you like, that's r minus 1 squared. So our roots were repeated roots 1 and 1. And so that's an example of where we said, oh, you have to have that factor of x. So we've already seen an example of where it works. Later on, in the videos at least, we'll talk about why it works. But for now, we just say, okay, repeated roots have a correcting factor of x involved. And now we've solved every constant coefficient, homogeneous, second order, linear differential equation. See, if you just add enough assumptions, then you can succeed. Great. So to demonstrate, let's do an example. Solve the following. 2y double prime minus 7y prime plus 3y equals 0, with y of 0 equals 1 and y prime is 0 equals 8. All right, so what do we need? Well, we have a second order differential equation and some initial conditions. We're in our nice setting. We're homogeneous, linear, constant coefficients. So first step is do the algebra problem. So this becomes 2r squared minus 7r plus 3 equals 0. So be careful here that y becomes 1. So essentially you should think of the order of the derivative becomes the power of r. Second derivative, second order, power 2. First order derivative, power 1. 0th order, power 0, which is a constant. Now you have 2r squared minus 7r plus 3 equals 0. And you have two options. One option is you can say, I'm just going to go for it. I think I can make it factor. And if you can see that, that's awesome. And I'll tell you, it does factor. This factors as 2r minus 1 and r minus 3, I think. Let's see, does that work? Let's check it out. 2r squared, that's good. Minus 6r minus r minus 7r and plus 3. Now, if you're like, I don't think I can do that, that's fine. We'll give you another option, right? It's okay. You don't have to know every way. You just have to know a way. And we give you options so that you can find the way that works best for you. And oftentimes it's good to have several things ready to go. So of course, what's your other option is to say, well, quadratic formula. Negative b plus minus square root b squared minus 4ac. So 4 times 2 times 3. Now let's just write that out. All over 2a. So don't forget the 2 times 2. Now, over here, we would say our roots are a half and 3 because we set each part to 0. Do we get the same thing here? We better. That's the theory, right? 4 times 2 times 3 is 24. 49 subtract 24 gives us 25. And it turns out, square root of 25, true story, it's 5. All right, 7 plus 5 is 12. 12 divided by 4 is 3. And then 7 minus 5 is 2. 2 divided by 4 is a half. So we end up with the same roots. Now, these are distinct roots. And so that tells us that our solution has the following form. Namely, all solutions to this differential equation have the form some constant e to, doesn't matter which one goes first, 3x some constant e half x. And so the rest of the problem, now that we know what all solutions look like, is going to be solve for initial conditions. Now you might say, wait, did we really solve a differential equation without doing any integration? Yes, Because we have theory. And once we have theory, that saves a lot of work. And you're probably thinking, are you being serious with me? Yes, I am. Very serious with you. No. We're just, once you have the right tools, then you can use them and life gets better. And so that's why we have these tools, because then we have a way to solve things. All right, so let's look at our derivative. That'd be 3a e to the 3x plus 1/2 b e to the 1/2 x. And, well, what happens? We need to plug in our initial condition. So y of 0 should be 1, because that's what we're told. But if you plug in 0, the nice thing is e to the 0 is easy to compute. That's a plus b. Y prime is 0 should be 8. That's what we're told. But plugging in here, we should have 3a plus 1/2 b. And now we're in our favorite setting. 2 equations, 2 unknowns. And so we start thinking, well, what can we do? And the answer is we can do a lot. Do you want to cancel a's or b's? And I do like cancellation more than substitution. So let's write this again. I'll write it in a slightly, I'll stack these here. A plus b equals 1. I don't like fractions, so I'm going to go ahead and multiply through by 2. So if we do that, that'll become 6a plus b equals 16. And now let's do some combining. And since they both have b, that's going to be pretty easy to cancel. I'm going to subtract the top one, add the bottom one. 6a and a minus a makes 5a. b minus b makes no b. And 16 minus 1 makes 15. And so a is 3. Now we know a, 3 plus b needs to equal 1. So what does that say about b? Well, subtract 3, b is negative 2. So putting in our values for a and b, we get that our solution looks like 3 e to the 3x minus 2 e to the 1/2 x. And that's our answer. We're done. We're done. And we're going to do a lot more of these. So come back and we'll see you again.